In this video, we're going to derive electric field due to a point charge. So in this setup right here, we basically have our point charge, which we're going to say has a charge capital Q. Now this is the charge producing the electric field. And this charge is basically our test charge that's in the electric field. And we're going to say that it has a charge positive lowercase q. And we know that electric field, basically the electric field acting on our test charge is just the electrostatic force acting on our test charge divided by the value of our test charge. So just Fe over lowercase q. Now you might be thinking, as the value of our test charge increases, the electric field decreases, because basically we'd be increasing the value of our denominator. But that's not actually what happens, right? As we increase the value of our test charge, our electrostatic force will also increase. Because if you remember, electrostatic force is K capital Q lowercase q over r squared, which we remember from Coulomb's law. And so you can see, as the value of our test charge increases, our electrostatic force will increase. So as you can see, as Q increases, Fe will increase as well. And they increase, and they're proportional to each other. So really, as this one increases proportional to each other, so the electric field doesn't change. Right? And it turns out electric field only depends on the charge producing the field and the distance to our test charge in the field. So here's what we're going to do. All we have to do is we have to substitute what we have right here into Fe. That's it. Because, as you can see, this is equal to Fe, so we can substitute into there. And so when we do that, here's what we get. All right, basically I'm going to put Fe in parentheses. Basically this stuff right here. So K capital Q, Q over r squared. Basically this is what we have for Fe divided by our test charge lowercase q. And so you can see, right, you can see how our test charge cancels out. So really this charge doesn't matter when it comes to electric field, right? And so what we get from this is that the electric field is K capital Q over r squared. And so this right here is basically the electric field at this point in our electric field. So really, this doesn't even matter. We don't need to know what that charge is. It's just a certain point. It's a certain point that's at a certain distance away from the charge producing our electric field. And so you only need to know this charge producing the field and the distance from that charge producing the field. And that will give you the electric field at that point, basically. Now this right here, remember, electric field is a vector, right? This is telling us the magnitude of the electric field. And the idea is, if you recall, if this was a positive charge producing the field, then the electric field would go this way, right? If this was a positive charge, right, electric field would point that way. Because a positive test charge, if this charge is positive, a positive test charge would want to move away. So the electric field points that way. But if our charge producing the field was negative, then a positive test charge would want to move that way, right? This would be the direction that the electric field, this is the direction that a positive test charge would want to move towards if this charge is negative. So you can see how really we're just referring to the magnitude here. So we're thinking of the magnitude of our charge. So we're thinking this as the magnitude of electric field, because you just got to remember, electric field is a vector. This is just telling us the magnitude of the electric field. And so yeah, that's pretty much the whole idea of finding the electric field due to a point charge. That's basically what it would be.